Good morning or good afternoon, everybody. Again, welcome to APNIC e-learning web class. This is the second session that we are going to do for today, and the topic that we are going to cover is all about IPv6 addressing and subnetting. Now, a few housekeeping things first. Today is the 8th of January in 2014. This is the first day that we're back doing e-learning again. It's 12:30 in the afternoon from Brisbane in Australia, from where I am broadcasting this class. Now, to introduce myself a little, my name is Cheryl Hermoso. I work as a training officer for APNIC, and as part of the training team, it is our role to deliver workshops, face-to-face trainings to the members of the internet community in the Asia Pacific region. So you can see there the specialties that I do, the topics that we do cover are DNS, DNSSEC, Internet Resource Management, IPv6 of course, network security, and a lot of routing and security modules as well. Now, a brief reminder, this class runs for 1 hour, and at the end of the session, we will have a brief survey to let us know whether you have any suggestions on what topics we want to cover for the next time, and also what is the quality of the session that we've covered. Okay, so what are we going to do for today? We have 1 hour. For most of you, you already have a background and it's all still fresh in your memories because we just did that about a couple of hours ago. So we will be looking at more specifically at IPv6 addresses. This is something that I've introduced to you for 1 or 2 slides in the previous session. So now here, we will actually look at more closely into the text representation. We've discussed about how to trim it down, but let's try and give some examples and see different scenarios in how we can do those trimming. Also, we will look at the IPv6 addressing structure and address management hierarchy. Okay, I think you've seen some of the slides already. And then we will look at the different types of actual IPv6 addresses. This is something that is confusing to a lot of people because, well, you will see later on that actually in IPv4, you assign either a public or a private address, but you assign only one IP address per interface. You will see later on as we move on that you can actually assign more than one IP address to a single interface. And you can have a local address, a global address, a linked local address there, maybe even a unique local address. So we will look at these things. What are the differences between them? Where do we use all of them? And what are their coverage? Like, is local address routable? Is global address reachable from everywhere on the IPv6 internet? Things like that. So where is the proper time to use which type of address? We will look again at interface ID and some examples on how you can get that from a MAC address. And then we'll look at how auto configuration works. So I've mentioned about stateless address auto configuration earlier. So we'll look at how the process actually works. What are the different commands or different messages that are being passed through when you do something called as neighbor discovery. All right, and then towards the end, I usually don't have enough time to cover subnetting, but what I'm going to do is just give one example. Okay, we'll try to work on a subnetting example, and then I have 1 or 2 exercises that you can do on your own. All right, so that's what we're planning to cover for the next 1 hour. I hope you're all with me and are ready to learn more about it. All right, let's start with IPv6 addressing. Just to recap again, what is IPv6? Of course, IPv6 is the newer version of the Internet Layer Protocol in the TCP/IP protocol suite. So the current IP protocol that we're using is IPv4, and we have IPv6, which is intended to, not exactly to replace, but to complement the currently existing IPv4. And the main reason for that, what is the main compelling reason for IPv6? Simple, we are running out of IPv4 addresses. Okay, there are other reasons, of course. It also has introduced many functional improvements. It shows a more simple header, faster performance, gives us a bit of more security. But of course, the most noticeable change is the increase in the address space. This means that we will have more hosts. In IPv4, we have 4.3 billion addresses. In IPv6, we can have way more than that. So that's actually, if you want to quantify, that's 2 raised to 128. So which is this one. And if you try to read through this number, I don't even know how to pronounce or what do you call this, but it's that big a number. Okay, so the way we write an IPv6 address, it's 128 bits. It's not really very easy to write down that much and for us to remember more. So what we do is we use hexadecimal digits. So when you say hexadecimal, that's 0, 1, 2, 3, 4 up to F. Okay, so each hex number is actually a representation of 4 binary digits. Okay, so 4 bits, or what we also commonly call as nibbles. So you'll see these a lot when you go through mailing lists and all that. You'll see people calling it as nibbles rather than 4 binary digits or a hex digit. So with that, since we have a hex number, so we can now have 32 hexadecimal digits instead of 128. So somehow we've already trimmed it down. It's something that we can read through, we can write down with less errors than 128 bits. Now this is an example of an IPv6 address. Earlier I've shown you a proper complete IPv6 address, but this one is also correct. We said that 32 hex digits should be a representation of your IPv6, but how come this is correct? Okay, we will see on that as we move on. So just to clarify the nibble thing that I've mentioned about, so this is one field in an IPv6 address, so A910, that's one field that is equivalent to 16 hexadecimal digits. So if you convert that one, will be something like this. Okay, A is 1010, 9 is 1001, 1 is of course 0001, and 0 is 4 zeros. Alright, so this is a valid IPv6 address. Notice it's 2001. Later on, when we discuss the different types of IPv6 address, try to remember this address and see whether it belongs to which category or which class. Okay, some of you have seen this slide, so we'll just go through this really quickly. So you already know by now, it should be very clear that an IPv6 address uses 16 hexadecimal digits and they are divided into 8 fields. Each of the fields are subdivided or separated by a colon. We don't use dots, we use colons. Okay, so this is our example that you've already seen before. It should have 8 fields, and if you count the number of hex digits there, that should be 32. Now we've already talked about abbreviating the IPv6 address. Why is that? What is the purpose of abbreviation? It just makes things easier. Well, your computer, maybe your operating system, your networking equipment can do it themselves, right? You can write down the whole thing and it will trim it down, or it can expand it themselves, but just makes it easier for us, like humans, to actually either write it down, or when we're configuring our routers, it's easier and faster to have something that is with less zeros, so to speak. So what are the different ways? I can only see 2 here. One is if you have a leading 0. So if you can see this, for AED, that's our example, notice that as a leading 0. Okay, so this one, so you can see this, that is a leading 0. You have 2 zeros there. Okay, so let me just try and do this if that will work out. So let's try to remove that. Yep. And then what else? You have this here. You have 3 zeros. You can remove this. 3 zeros. You can remove this. Another one. 3 zeros. Just remove that. This 0 can be removed. How about this one? Can you remove 0 in 1250? Obviously not. And also 2B00 should remain as 2B00. So the answer or the result after you did remove all the leading zeros should be this second line. Okay, notice here that you've already removed 00 from 00 to 3. Now another thing that you can do, which is the most common one and probably how IPv6 came to be commonly seen as the double colon symbol, is because of this. If you have groups of zeros, meaning if you have fields of adjacent zeros, what you can do is remove all of those zeros, okay, such as this case. You can see it very clearly here. So you can remove all those adjacent, okay, only adjacent zeros, and then replace them with a double colon. Okay, so here you have 0, 0, 0, that's 3 fields. You know that this is a representation of 3 zero fields, or 12 hexadecimal digits that are zeros. Alright, so I have a question. It says here that null values can be used only once in an IPv6 address. So what if, let me try and remove that first. Okay. What if I have this example? So I'm gonna write something down. Maybe I should just write them on the chat. Might be easier. Anyway, let me try here. So let's have 200. Say let's just use this. Let's have this one. Can you see this? So I have this example, 4ED 23, then you have 3 zeros there. There's a typo, sorry. Okay, let me just write them down in the chat, easier. That's 4EED 23 0 0 0 36E 0 0. Okay, so what are the different ways that you can trim down this IPv6 address? Take note that it says here that null values can only be used once in an IPv6 address. That means you can only use double colons once in an address. So where do you put them? Do you put them in this field, like the one with the 3 zeros, or the one with 2 zeros? Okay? The answer should be, well, you can do either way. In most cases, you would want to trim down the ones with the most number of zeros. So with this will be 4ED 23 colon colon 36E 0 0. So this is an acceptable answer. Well, this is the answer that I would prefer. However, nobody is stopping anyone to use this one, 0 0 with 3 zeros, and then 36E colon colon. Right? So that is also a correct answer. Now, when do you use which one? If you look at the RFC, based on how people are using it, all right? If you get, let's say, a network prefix and you want to use that to, say, you want to use a double colon to separate your network prefix and your interface ID, then that's a good way to use it. So it doesn't matter if there are other zeros in between, but you use it to separate your network prefix and your interface ID. Another way is, this one is based on the RFC. I'm not sure if I have that here. I probably don't, but says that you have to replace the rightmost double colons if you have multiple possible options. Okay? So that's what you do. So this is just to show you how big the IPv6 address is, how many zeros and how many bits that you have there. So that's easy. This is the IPv6 addressing structure. So let me just repeat what I said in the previous module. So why is this important? Why do we need this? This addressing structure is important to understand the entire IPv6 address space. You know that you have 128 bits from 0 to 128 here, and you would know that we will subdivide them into two. One part will be used for your network prefix, the other part will be assigned by your hosts as your interface ID. The smallest subnet that you can create is a /64, which is the smallest prefix here that you have for your network prefix. All right. So if you are going to assign, maybe you have a LAN, a local area network, and you have 10 or 20 computers there, or maybe even more. Okay. A single /64 gives you how many possible addresses? That's 2 raised to 64. So that means that you can have 2 raised to 64 hosts in a single subnet. So it might look like, it might seem that it's wasteful if you're going to assign the entire /64 for, let's say, 5 or 10 computers. Okay, but that's how it is right now. Okay, there are some limitations, especially in operating systems, where you cannot assign anything that is smaller than a /64. So based on people's practice, best common practices, we use /64 to assign to a single subnet, no matter how small it is. Okay, now this part is all for the delegation. Delegation is coming from the hierarchy, from top, which is IANA, going to the regional internet registries, going to the local internet registries. If you have a national internet registry that also sits somewhere in between your LIR and your RIR, and then trickles down to end users and sites, could be, let's say, an academic network, could be a government office, could even be, let's say, an enterprise, a multinational company. Those are your end sites. Those are your final customers. They are the ones that are actually using the IP addresses. So how do we go about this? So we have this whole prefix here. We assign /32 coming from ISPs. Well, actually from IANA first, they will get, each of the RIRs get a /12. So /12 should be somewhere on here. Okay, now each of those /12s, from each of them, RARs would give /32 to customers. So you have /32 here. Now that's not saying that you can only have /32 and that's the maximum that you can get. If you think about it, /32 is already a very huge number. Hang on, this is already the size of the IPv4 address space. Is that correct? And we are using it to assign only to one ISP. Okay, so actually when you do addressing, subnetting, and even your address planning later on, there should be a shift in the mindset somehow. The difference between v4 and v6 at this point is that IPv4 is a scarce resource. IPv6, we have plenty of them. So your goal in IPv6 is not to conserve. Of course, it goes without saying that you should still only make use or make delegations when it is needed, but your main concern is not conservation, it is aggregation. What is aggregation? So when you are an ISP, if you have many customers, all of them, maybe you gave them /48s or /64s each. Now, when you announce this onto the global routing table, aggregation means you are combining all these adjacent blocks into one and announcing it as a single prefix. Okay, you're announcing it as a single prefix. That is aggregation. So that's your main goal in IPv6. That's because there is a very big chance, there's a very big likelihood that if we're not concerned with aggregation, your IPv6 routing table will spike up, will grow very huge because of the amount of available IPv6 address space. Okay, anyway, going back to this, you will get a /32 IPv6 block from your RIR, and from there you distribute blocks to your customers. the size that we usually give is from /64 to a /48. So let's just say that you're giving /48s to all your customers. Okay, the policy is based on you. There's no specific policy that tells you to assign /48 for a specific size of your customers. It's just based on the practice that is being used by people in the industry. But so it's from 64 to 48. But let's just say that you are actually giving /48 to all your customers. What does that imply to you? You can have 2 raised to 16, okay, customers, each of them having a /48. So for a big ISP, that is really not enough. Okay, so you can actually come back to APNIC and request for a subsequent allocation or another /32 block once you've reached a certain point of delegation. Okay, when you do that, APNIC will provide you with another /32 which is adjacent to your previous block. So you will now have a /31. Okay, that's how subsequent allocation would work. So don't worry about, let's say, if you're giving /48s to all your customers and you can only have 2 raised to 16 customers, because that's really small. But you can always get a subsequent allocation. But of course, in some cases, I see this in a lot of ISPs, they have a tendency to give out /64s. Now, this is not bad. It always depends on your own policies, but consider how these networks would grow in the future. Okay, think about their growth. If they're not expected to grow, then probably that's okay. But if there's a slight chance that they will need another, say, another subnet, okay, maybe they need 2 networks, one for financing, one for their tech team, if it's a small company, something like that. So you will want to give them more than that, because in the long run, when you do your address planning, if you'll have to allocate another blocks to them that is not adjacent to what they currently have, either you end up with this contiguous subnets, or you will have to renumber, which is more painful than actually planning it now. All right, so that's how you do it. So it's from /64. If it's very small, you can have a /56 if it's something like a small to medium-sized company. And for big companies, you give /48s. Any questions? Notice here that we said devices get 128 bits because this part is what you assign to your to each of your network, or to each of your hosts. Okay, so I've mentioned something about allocation and assignment earlier. So just to make sure that we're all on the same page, this is what allocation and aggregation and assignment is all about when it comes to IPv6. Depending on what your current membership is, you might get an allocation and you might get an assignment. But what's the difference between both of them? Allocation is when you get a resource, whether it's v4, v6, or AS number. When you get that resource, you are going to use it to further subdelegate to your customers. So if you're an ISP and you are requesting from APNIC for subsequent delegation to your customers, then that is considered an allocation. You will get a /32 maximum IPv6 allocation by default. And from there, okay, it's actually this one. And from there, you can do your sub-allocations, maybe sub-allocate /40 if it's big, sub-allocate /48s to your customers, okay, or /64s if it's very small, okay. So that's the difference between allocation and assignment. But you can also see something like portable and non-portable here. So when you say portable, that is something that you get from an RIR, something that you get from APNIC. So this one is portable, even if it's an assignment. Let's say we have members that are from academic institutions, governments, and also multinational companies. So when you get that assignment from APNIC, meaning assignment means you're going to use it for your own infrastructure. Okay, you're going to use it to assign to your network. So that's assignment, but it's portable if it's coming from APNIC, and if it's not portable if it's coming from anywhere else. Maybe it's coming from your upstream provider, then that is non-portable. We've already talked about the IPv6 addressing models, unicast, anycast, and multicast. So just a review of what this is. Unicast is single interface going to a single interface. So you have a unicast source address and a unicast destination address. Anycast is when you send packets. It's not sent to just one. It's not addressed to just one. It is addressed to a group, what we call as an anycast group. However, only one member of that group will be able to receive your packet or your message. So your source address is unicast, your destination is an anycast address, and multiple interfaces have or share the same anycast address. Only the one that is closest will get the packet. And how do we know which one is the closest? That depends on the routing protocol that is being implemented. All right. Multicast, on the other hand, is from single interface to multiple interfaces. So all of them will receive your packet. So you don't have to replicate each and every packet and send them individually to each of the members of your multicast group. Okay, so just remember these three: unicast, anycast, and multicast. And as we go on, we will be discussing the different types of IPv6 addresses. Notice that most of these are unicast addresses, but towards the end, I think I have a few that is using multicast. All right, any questions so far? So now we are actually going into the IPv6, different types of IPv6 addresses. Okay, so something that you are familiar with IPv4, and let's try to compare them to IPv4, just for simplicity's sake. Now, what are the more popular IPv4 addresses? We have a loopback address. Okay, loopback address for IPv4 is 127.0.0.1. Why is that selected? Well, we don't know. Now, in IPv6, we also have a loopback address. Okay, that is ::1/128. Does anybody understand what that is? So that's just one, okay, and the rest are all zeros. You have 127 bits that are all zeros, and then the last, okay, the least significant number is a 1. Okay, so that's why we're using a double colon. So we're actually abbreviating this. Now, all IPv6 addresses are never complete without its corresponding prefix. So here we said it's /128, so that it refers to only one IP address. Now we have another one called the unspecified address, which is : /128. That's just equivalent to all zeros. In IPv4, we have an unspecified address 0.0.0.0. We don't usually see them, but that's the very first IP address that is assigned to an interface when, let's say, you're booting up your routers or you're booting up your host. That's the very first address that it gets before it pulls out something that's maybe coming from a DHCP server or something that you have manually assigned. Okay, we have two very common IPv6 address prefixes that are used before for mapping IPv4 and IPv6. That means, like, we have in a single address, you can easily port out the IPv4 addresses, okay, even if you're given an IPv6 address. What is the purpose of this? It came in very handy during the early days when we are still doing a lot of migration. So if you have, let's say, maybe you wrote a code, and this code can only do IPv4. So it's very hard to recreate everything, create all these other, basically create a similar code that is only for IPv6. So for compatibility's sake, if you have, let's say, a program that's running and you're not sure whether it's going to go through v4 or v6, we use these types of addresses. So you can easily pull the last part or the last 32 bits and that is your IPv4 address. So you have IPv4 mapped IPv6 address, that's ::FFFF/96. Why is it /96? Easy, because the last 32 bits is your IPv4 address. So normally you actually see that as written as ::FFFF say 192.168.1.1, something like that. But of course, when your machines read it, it will convert everything into binary anyway, so that's still an IPv6 address. If, let's say, you can create a variable that only gets the first 32 bits if you are running via v4, or it will get the entire thing if you're running IPv6. All right, so that's the purpose of these two. One of this is already deprecated. IPv4 mapped address has been deprecated and just replaced by this other one. What else? There are, well, you've already looked at and specified and loopback addresses. Now we will be looking more closely into these 4 address ranges. Now, the reason I wrote them down here as a list is so that you can familiarize yourselves with the different types of IPv6 addresses. Okay, so if you see an IPv6 address, you know already where it belongs. So with specific groups, global unicast address is 2000/3. Okay, it is defined. So notice the network prefix here. That is the number of bits that represents your range, or your, let's say in this case, your global unicast addresses. So 2000, meaning first 3, that's 001. So if you convert that into hex, you need the 4 bits, so that's 0010, which is equivalent to 2 in hex. Okay, you have link local address, which is defined by the first 10 bits. So first 10 bits, so that's all ones here, and then you only have up to, that's 8, that's 10. So F, this is E, this is 1000, so that's 8, and then F0 for the rest. So FE80 : /10. You have multicast address, which is FF00/8. So remember this one because we will be using this for the neighbor discovery process. And you also have something called unique local address, which is on the range of FC00/7. Now let's look at them more closely. All right. So the very first one that I want you to be familiar with is the link local address. If you see anything that has FE80 in its address, you should instantly know that's a link local address. I think I've mentioned this before, but once you've enabled IPv6 on your machines, if it has support for IPv6, then automatically it will have an IPv6 address. The interface ID, you already know how you get it. That's based on your MAC address. But the network part, the network prefix part, you would notice that it starts with FE80. Okay, so that is your link local address. It's a special address assigned automatically, and it is only available for communications within the local link. Thus, the name link local address. What does that mean? You cannot use it beyond routers, beyond L2 or L3 devices. Okay, it can only be visible to all of the other hosts that are in the same subnet or are in the same network. Okay, so the good thing about that is you don't have to configure anything. You already have an IP address. If you want to exchange information in between the routers or the hosts in that same subnet, you can do so without configuring anything. Okay, that is your link local address. Again, just note that it will never pass through a router. All right. The next one is a unique local IPv6 unicast address. So simply, you can just call it as ULA for unique local address. You already know that it's IPv6. You already know that it's a unicast address. You can just remove that part. Now, what is a ULA? ULA is something that's similar to your RFC 1918. Okay, RFC 1918 defines all the private addresses. In IPv4, what are our private addresses? You have, of course, 192 range, you have 172k/12, and 10.0.0.0/8. Those are private addresses. They're not supposedly viewable on the global internet. You're not even supposed to announce those prefixes because it can only be used within your local network. Okay, that is RFC 1918, private addresses. Now, if you talk about IPv6, ULA can be considered as equivalent to RFC 1918. You only use it for your local network. You can use that to assign to your interfaces, but it should not be visible on the global IPv6 internet. All right. Now, before we had ULA, we had something called a site local address, or SLA. Site local address has the same idea, so it's local only within a site. So if you have a local network, that can be a site. If you have, let's say, your entire ISP network, that can be a site. If you have a wide area network, that can also be considered as a site. So there's a bit of confusion with that. There is a problem with the definition of site. It's vague, it's ambiguous. How do you actually define a site? So if you have a smaller site and it's part of a bigger site, then you will have conflicts of IP addresses. So in replacement to SLA, or site local address, they came up with ULA. So the idea or the goal is the same. It's only for use privately. But if you check anywhere around the world, it should be unique. Okay, that's a defining factor. It's a unique address anywhere on the internet. Okay, although you only use it for your local assignments. Okay. Now, how do we make sure that it is actually unique? There's an algorithm that's defined in the RFC as well on how you can do that. You can have a look at these websites, and it's a form. You can generate unique local addresses using these addresses. Okay, the next one is the global unicast address. Now, this is perhaps the most important for us. This is the one that is used for routing. It's routable addresses, the ones that are announced. These are the ones that you use to announce to your servers, to your, say, border routers, anything that should have a global visibility. So the range that we use for global unicast address is 2000/3. Okay, again, the defining what defines this range is the prefix 3 here. So that's 001 and then all zeros, and then up to 001 and then all ones. So this is your actual range. You have 2000/3 all the way up to 3FFF, FFF, all of that is F/3 as well. Okay, you already know this. All 5 of the RIRs were given a /12, okay, from that /3, which gives us 506/12s left still in the global IPv6 address pool. Okay, that is your global unicast address. You use that to assign to your publicly available interfaces. We also have something called 6-to-4 addresses. Now, in the early stages of the development of IPv6, we want to make sure, of course, that there is compatibility with IPv4 and IPv6. But that's the thing. IPv4 and IPv6 don't exactly work together. They are not backwards, nor are they forwards compatible with each other. If you have an IPv4 host and then you have another IPv6 host, there is no way that you can exchange packets or data in between them. Okay, so that's a fact that you have to understand very well. So the way that you do with migration is you have an IPv4 network, you start adding IPv6 there to each of the hosts, and if other networks or other hosts don't understand IPv6 yet, then you have a backfault. You have your IPv4 to communicate to them. So it's like you have two IP versions that are running. You have two IP networks that are running, IPv4 and IPv6. Now, what if you want to send from IPv4 host to an IPv6 host? What if you're running an IPv6 only network and you want to reach a website on the internet that's running only IPv4? So that's something that we will discuss with transition. But we use a lot of these addresses. 624 addresses, that's 2002/16. So try this. If you have access to a public server, a public IP address before, and then you can get maybe access to a broker, okay, an IPv6 broker, and they can give you an IPv6 range that you can use to connect to their IPv6 network, okay. Things like 6XS or Hurricane Electric, try those ones out. So when you, let's say, sign up to these things, you will get an IPv6 block, and notice that it uses a block that is within this range, 2002. That's because that's the block we're using for any tunneling mechanisms, 6 to 4 mechanisms. Okay, so that's the value with that. Now we have other blocks that we use for documentation and also for examples. So if you're reading books, if you're reading journals, you should notice that they wouldn't use actual IPv6 addresses, because that can be catastrophic if people want to try it out, and it can end up messing the internet at some stage. Then that's not good. So we provide documentation blocks and also example blocks. We use 3FFF, FFF/32, and 2001DB8/32. Now this second one is what you would most commonly see in examples. In our case, when we create exercises as well, we try to use these documentation prefixes. There is a similar one for IPv4, so just try and find it out. So it's not something new with IPv6 only. IPv4 also has documentation blocks. Any questions with the different types of IP address blocks? So what we've covered, we have a link local address, which you use only for your local link. It's automatically assigned. We have another one called a unique local address, okay, that is used for private networks. Okay, we had SLA or site local address, but that has already been deprecated. What else? We have 6 to 4 addresses, global addresses. Okay, we've already discussed them. The thing is, you can see not just perhaps one family, but you might be able to see one interface that contains multiple types of IPv6 addresses. So it's possible that, of course, automatically any interface that's enabled will already have a link local address. That is mandatory. You cannot change that. Now, apart from the link local address, you will want to assign a unique local address perhaps. Or if it's a server, then you will probably want to have also a global address. So notice that that's already 3 IPv6 addresses only for a single interface card, right? And even with just one type of address, you can have more than one. So say a global address, you want to assign them from 2 different IPv6 prefixes. That is also possible. Okay, so that's a very huge difference than what we are familiar with in IPv4. Any questions so far? None? So next one is your interface ID, which most of you are already familiar with. Now, interface ID is the second half, or the lowest, or the 64-bit half of your IPv6 address. We assign them normally either manual configuration. We can assign them via DHCP, but the 2 most common ones are to use EUI64 and also using pseudo-random numbers. Depending on the operating system, okay, they have different defaults. Microsoft Windows operating systems normally, I think, use pseudo-random numbers. the latest versions of Mac OS X also uses pseudo-random numbers, but a lot of Linux machines, Unix machines, and older versions of Mac would be using EUI64. Now, let's just recap a bit. What's EUI64? So, we have a MAC address, a 48-bit MAC address. A MAC address is a physical address that is unique to to an interface, right? To any host. So from that's 48-bit, we will generate a 64-bit EUI64. I think I have that here. Yes. So let's take this one for example. So this is a very simplistic example. So this is your MAC address, that's 48 bits. Now you want 64 bits out of that 48 bits, so you will have to add something there. So what we do is subdivide that into two, okay? The first upper half and the lower half, and then somewhere in between you add FFFE. Okay, so very simple. You don't add anything there, you add only FFFE. So it's actually one way to spot whether you're using EUI64. If you see something like FFFE, then most likely, okay, most probable than not, then that's probably using EUI64. So yeah, you add that, and then the reason it's called modified is because of this. You check the 7th bit. Okay, it's 7th bit from the upper half, and then you toggle that from 0 to 1 if it's for a unique address. Okay, so in our case, we toggle that to 1. That's why we have, instead of 00 here, we have 02. Okay, and then you have FFFE in the middle. So this is the address that will go into the interface ID part of your IPv6 address. You will still need the network prefix, which is either one of those address ranges that we have discussed so far. All right? Now let's just look back here for a second. I've mentioned that EUI64 is probably the most common one, and the other one is using pseudo-random number. And that is because of privacy reasons. So if you want to have a look, I forgot the RFC number, but something about privacy addresses in IPv6. So the reason for that is with EUI64, it's based on MAC address, which is essentially something that's unique to your machine. So whether you're here or whether you're traveling halfway across the globe, you will end up with the same interface ID. And if someone is snooping or trying to locate you, then they can probably find you if you're, of course, if you're visible on the IPv6 internet and you don't have all your firewalls and everything. But yes, it's easier to locate you, and it's could be a privacy concern to some. So instead of using or basing on something that is unique on your machine, with pseudo-random numbers, your operating system will just generate a set of random numbers and then assign that to your interface. Okay, that's the purpose of that. In the future, there might be other ways that we will be using to assign the interface ID, but so far, these four are the common ones that we are actually in practice using now. Now, let's look a bit on zone IDs. Now, how many of you here already have IPv6? Well, if you're running any latest versions of your operating system, of course, you will have IPv6 already supported. So it's actually on by default. So if anyone here has the IPv6 on and supported, can you try and do ipconfig or ifconfig? You will see your IPv6 address. Okay, you will probably have a link local IPv6 address along with other things like Teredo and stuff. But just notice that in Windows, more specifically, you will see something like percentage and then a number. Okay, this is different for different operating systems. On Mac OS X, I think it's EN0 or EN1, so depending on which interface it's occurring. But in Windows, it's percentage and then a random number. So what's that for? We mentioned earlier that you can assign multiple IPv6 addresses on a single interface. So how do you know where your packet will get out or where it's coming back in? That's the purpose of zone IDs. So if, let's say, for example, here what we have is you want to send a ping command Okay, a ping request perhaps to host B from host A. Host A's IP address ends with 4121. Host B's IPv6 address ends with 3001. So I'm in host A. I want to ping host B, so I ping 3001. But I won't put his zone ID. I will put my zone ID. So see, you're using %4 and not %3 because that is my zone ID. I am host A. That means that my packet will go via this zone and nothing else. Okay, zone IDs are unique in each well, not just operating system, but in each machine, and it's just locally defined. There is no way for host B to know which zone IDs you're using. It's just locally defined. Okay, so just to make that one clear. Now let's go and have a look at auto configuration. So now that you already have an IPv6 address, maybe you've assigned that to your interfaces, you understand how that works. Next thing there is, how do how do hosts find each other in an IPv6 network? How do you do that in IPv4? In IPv4, okay, in the lower layers, okay, in your link layer, before you can send something on layer 2, you should know the MAC address. In the IP layer, you know the logical address, you know the IP address, right? You need to be able to find the MAC address to actually send that via layer 2. So you use something called ARP, or the Address Resolution Protocol. That is in IPv4. In IPv6, well, it's something similar, but since we don't have broadcast, we will be using what we call as Neighbor Discovery Protocol, and it uses the ICMP protocol. Okay, it passes through ICMP to find those different hosts on the network. Okay, so what do we use Neighbor Discovery for? One is when you want to assign a link local address to your machine. You need to check whether there is a duplicate anywhere in your local network. Another one is when it will get a unique local address, or probably even a global address. It will look for maybe a DHCP server or a router running an advertisement to get those network prefixes. Okay, so I hope you understand where I'm going to. So the way you assign an IPv6 address can either be using stateless or stateful. That's very easy. When you say stateless, that's when you're not concerned with the actual address, so it can be assigned via say Slack or stateless auto configuration, which we've discussed. And then you can also always still go with stateful mechanism, such as using DHCP servers, or you can assign that manually as well. So let's just say that you're getting your IPv6 address via a router advertisement. First is when you turn on a host, what happens? Of course, it will try to get an IPv6 address, right? It's link local first, and then global or unique local address. So link local first. It will have a tentative address. It will be assigned to the new host. We call it a tentative address because, well, this is your to-be link local address. However, you are not sure whether there is a duplicate anywhere on your network. So that's still a tentative address, and then you will have to check with everyone else. So our tentative address here uses EUI64. Did you notice that? This is a link local address very easily because it uses FE80. It is using EUI64 for an interface ID because you can see that it has FFFE, right? That's the way to easily spot it. So that's your to-be IPv6 address. So what you do now is to check whether it is unique, send a query to everyone. So this is part of what we call as a Neighbor Discovery Protocol. You're sending a command or a message called the Duplicate Address Detection, or DAD. Okay, Duplicate Address Detection. Now, first, when you do that, you do the message that you're sending out is a neighbor solicitation message to check whether someone's using that. Notice that we are sending it to a multicast address. everyone that's on your network, okay, uses or is part of a multicast group. Okay, this is what you call the solicited node multicast address. So that's the address that's where all of these are also part of. Notice that's FF02. Remember, our multicast address range is FF00. Okay, so again, that's a multicast address, and then you send your query, your neighbor solicitation message to that, and if anyone's listening and if anyone's using it, then they will reply. If you don't get a reply after a period of time, if you don't get a neighbor advertisement, that means it's unique, and you can now assign that address to your interface. Okay, any questions? Next, so you have a linked local address. The next step is, of course, to find either a unique local address or a global address. So here, I think we're getting a global address. How do we do that? Who gives, how do we assign a global address? You check whether someone is announcing a prefix, okay? And then, of course, the interface ID is you assign it to yourself. So you check for what we call as router advertisements. If you have a router such as this one, okay, it may be advertising your network prefix. Notice here it says that our network is using 2001:1234:1:1/64. That's our network. So if this is assigning router announcing advertisements, it should be using that prefix. So what you do, you send what you call as a router solicitation message. It will be sent to a multicast group. But it's no longer the solicited node multicast group. Okay, it's no longer using that address. It's now sending it to another multicast group, which is for all the routers. So all routers are listening here, and if one of them is announcing or advertising a prefix, you would know. So you send that to FF02::2. After that, the router will reply with the router advertisement message, okay, containing the prefix, this prefix, okay, only the network prefix, and then you assign it yourself based on the network prefix and based on how you will assign your interface ID, either using EUI64 or a pseudo-random number. All right, so that's basically it. So now you have two addresses there. You have your linked local address and you have your unique address. Did you guys follow that? It should be quite easy. I think the thing that you want to see here is what types of advertisements or what types of messages are being passed through, how it's done, and also to where or to which multicast address it's going to. Okay, so it's 1:30. We're supposed to be ending soon, so just give me another 5 minutes perhaps, and then we'll discuss subnetting. And then after that, I'll give you some exercises that you can actually just do by yourself, okay? So subnetting. Subnetting in IPv6 is no different than subnetting in IPv4, okay? So if you know how to subnet in IPv4, you know how to subnet in IPv6. But there's a catch here. If you are subnetting in IPv6, notice that you're using hexadecimal digits. So if you're you might get confused if you're just starting out. You might get confused whether you're working on hexadecimal digits or you're working on binaries. There are some stages where you might want to convert to binary, but don't forget to convert that back into hexadecimal digit. Okay, so let's look at an example. Here we have 2001db8::/32. This is the IPv6 block that is assigned to provider A by the regional internet registry. From there, provider A decided that they will assign /48 blocks to the customers. Okay, just to make it easy, let's just give /48s to each one of them. So how do you do that? If you're the one assigned in your company to do the subnetting, how will you do it? You can always, of course, use the calculator, but it is essential that you understand the how it works, or the concept behind it. So here you have your original block. So what you need is /48, right? So what do you need to get from 32 to 48? So that's another field. That's just extra 16 bits. So you try to extend your block to add that extra field there. So from there, that's your network prefix. This is just a side, like how many /48s are there in a /32? So how do you compute that? Simple, something like this, similar to what you do in IPv4. So you can have 2 raised to 16 /48 blocks in your /32 block. But what we're looking for here is only the first 4. So let's make things simple. Find the first 4 /48 blocks. So from here, you have your /48. You just manipulate the part in between your network prefix and your required prefix. Okay, again, similar to how you would do it in IPv4. So here, this field is what you will be manipulating. So convert that into bits to make it simpler. Once you already know what you're doing, you don't really have to do this step because you can easily spot how to do it. It's just incrementing. So anyway, going back here, you convert that into bits. So that's 16 zeros. And then you do your increments from there. So 000, 001, 0010, 0011, right? So you have it. That is your first 4 blocks. However, some people just stop here and then they just write down 2001 db8000. But you're just looking at this part. It's just one hexadecimal digit. What you need to do is to convert this back into hex. So you will convert the entire thing. So that will be 2001 db80000. So 0000, right? The next one is 0001. How about the third one? That's 000. Is this 10? No, it should be 0002. That's your hex digits. And the last one should be 0003. So that's your final answer. Those are the first 4 IPv6 blocks in the /32 block that we just gave you. Okay, so again, it's just a bit tricky if you're just starting out. Again, you might need to convert to bits at some point, but don't forget to write them back again into hexadecimal digits. Okay, so easy. It's very easy. So I have 2 examples here. First is asking for the first 4 /36 given a similar /32 block. And another one is looking for a first 4 /35 blocks given a /32 block. Okay, so if you're working on nibbles, it's quite easy. So the first one, this one, should be very easy for you to do. The second one, /35, it's not that easy, but it's still very easy. But yeah, try them both. And then if you run across a problem, do shoot me an email and I'll try to help you out. If you want me to verify that your answer is correct, please send me an email and I will do the same. Alright? Anyway, so I think that's the end of our presentation for IPv6 addressing and subnetting. So if you don't have any questions, I'll write down, I think someone's typing, so type away. If you have any questions, please feel free to ask them. While you're doing that, I'll write the link to the survey. So again, I'm asking everyone to please try and fill out the survey. It'll be very useful for us. If you want a copy of the slides, it will also be available to you after you've completed the survey. Alright, so I think we'll end there. I don't see anyone typing questions. I think it's just mostly thank yous. But thank you very much, everybody. I really appreciate you joining our class today. If you have any questions when it comes to getting your IPv6 address, please talk to us. Please talk to our help desk team and we'll be happy to help you out. Okay, that's it. That's the end of our session. Thank you very much, everybody, and I hope to see you